Okay, so today we're going to go ahead and talk about friction. So first thing we're going to chat about is static friction. So when I see this word static, I think of like stationary, not moving. So static friction is just friction that opposes motion when there is no motion. So it's friction that opposes slide when there is no motion. So it'll always balance out your pushing force until an object slides. So it balances pushing force until an object slides. So what I think about for that is, okay, so let's say I have like an old box, okay? So let's say I push it with a total force of 5 newtons and the object does not move. That means that our force of static friction will have to be 5 newtons the opposite direction. Same idea. Let's say I push it with a little bit more force. I push it with 20 newtons. And again, the object still does not move. Then that means static friction is pushing back in the opposite direction with 20 newtons of force. Let's say I don't push on an object at all, and it's just on a flat surface. If I don't push at all, static friction does not have to provide any resistance, so the force of static friction would be 0 newtons. There is always going to be a max value of static friction, of like the point until right before the object starts to move. So let's say I push this box with a force of 40 newtons, and it's just about starting to move. That is going to be the max value of static friction. So again, there's the min value of force of static friction is 0 newtons, and there will be some sort of max value. So the equation we use to calculate the max value of static friction, so this is force of static friction, I'll say max, is going to be mu times Fn. I'm going to call it mu s. So mu s stands for coefficient of static friction. And it's said kind of like a mu u, and it's the Greek letter mu. And again, FSF is the max value of static friction. And Fn, we know, is our normal force. Awesome. Friction. So kinetic friction, thus I think of the name kinetic, that kind of means movement. So it's a friction opposing sliding and motion. So friction opposing sliding and motion. So anytime there's motion, this is a friction that opposes that motion. And this force is constant. So the equation is going to be pretty similar to our static friction equation. It is going to be FKF equals mu K times Fn, where FKF is the force of kinetic friction, mu K is our coefficient of kinetic friction, and then Fn is our normal force. Cool. So let's go ahead and look at the units of mu. So I'm just going to put a little side thing. Let's find the units of mu. So it could be either mu K or mu S. Let's go ahead and look at the equation. Force of kinetic friction equals mu K times Fn. And sometimes people just call it the coefficient of friction and they don't specify whether it's static or kinetic, but you know from the context of the problem. So just a heads up, sometimes it's just mu times Fn. So we know the units of force are newtons. We don't know the units of mu, so let's leave that as a blank. Fn we know is newtons. Okay, let's solve for mu. So it's newtons divided by newtons equals mu. Newtons divided by newtons, that just cancels out, so that's just 1. So there are actually no units. It is a unitless quantity. Solve the problem together. using ideas of friction and our good old ideas for Newton's second law. So again, I would encourage you to solve this problem on your own first and then check back in on the video to check your work. So for this problem, again, we know the first step for any problem is always to draw a free body diagram. So I'm going to draw my free body diagram. So I have what? My good old 25 kilogram block. And I know it's pulled across the ground. It doesn't say what direction, but I'm just going to assume to the right, which I'll usually say is the right is the positive direction. So the force of pull is 400 newtons. Okay, I know friction opposes motion, so friction is going to go the opposite way. It is the coefficient of kinetic friction, so I know it's moving, so it's going to be the force of kinetic friction. Okay, it's on a surface, so I know the surface is pushing up on it, so I'll call that Fn. And then we know gravity always acts on things with mass, pushing it directly downwards, so the force of gravity. Cool. Again, let's just go ahead and calculate force of gravity. So Fg is going to be mg, so that's going to be mass is what, 25 times g, and again, g is always positive by definition, so that's 10. So Fg is 250 newtons. Cool. And we know the object is not, moving up and down in the y direction. Okay, so our next step after we draw our free body diagram is to do a coordinate system. And again, I'll usually say that the up and down direction, vertical direction is the y direction, and I'll say upwards direction is positive, and anything to the right is the x direction. So in this case, let's look at it. So the object is not moving up and down in the y direction. So that means our y forces have to balance out in this case. So in this case, Fn is just going to be 250 newtons. Cool. So great, I had lots of good things there. So let's go ahead and our next step in our coordinate system is again x and y, and then indicate what is the positive and negative direction. Cool. So our next step is going to be write out second law, Newton's second law, which is just F net equals ma. Cool. So we're finding acceleration in the x direction. So I'm going to write out Newton's second law in the x direction. So I'm going to go ahead and give myself a little space for that. So this is the x direction. So I'm going to call this F net x for the x direction, or you can just call it F net, but know that it's referring to the x direction in this case. So let's list the forces in the x direction. We have F pull and FKF. Those are the only two forces in the x direction. And again, I kind of like highlight in my head. This whole thing right here is the x direction. So I'm basically just listing those forces in the x direction. F pull, that is in the positive x direction. Force of kinetic friction is in the negative x direction. So I need to subtract those two forces. Again, we always know F net is mass times acceleration. F pull, they told us, is 400. FKF, I know my equation is mu k times Fn. Cool. So now our next step after we kind of write out the forces, use Newton's second law, F net equals ma to write out the forces, is we'll go ahead and plug in. Okay, so let's go ahead and plug in those good old givens. So I know the mass of the object in this case is 25. So we have 25 times a. We want to find the acceleration equals 400. Take away, let's see, mu k is 0.2 times Fn we know is 250. Cool. So we can do some good old math. 0.2 times 250 is just 50. What? 400 equals 25a. So then I get A, after a little bit of math, to be 14 meters per second squared. Cool. And let's check the thinking. So this is a positive number, but that makes sense because the object is accelerating to the right. So it should be a positive number. Awesome. Thanks for watching.